Well, the first thing we do actually, I would say, is that we don't really address the problem of intrinsically disordered proteins computationally, we do it experimentally. And then the question is, how do you interpret the experimental data? And as we are pretty much convinced that the data do not come from a single confirmation, we don't try and explain the data with a single confirmation, but we use what we think is appropriate description, which is a probability distribution. And the question comes, how do you actually define the probability distribution? Do you define the probability distribution analytically? You would like to be able to do that. Unfortunately, there are so many degrees of freedom and it's a heteropolymer in a very complex environment. This is very difficult to conceive of how you would do that. And so we take the easy approach, which is brute force, and that's simply to address the question numerically. This means, in our hands, what this means basically is to flood conformational space as broadly as possible. And if that doesn't explain the experimental data, then to try and determine how much we have to reduce that space in order to explain the experimental data. Now, there are many ways of doing that, and our method, I won't go into any particular details, but that's the philosophy behind it. But then I think the critical question comes, because there's been a lot of work now, I think, to try and understand how much conformational information we can derive from NMR data and other biophysical techniques from highly disordered systems. And so I think we're making progress in those directions using different techniques and different approaches. I think we are making progress. But I think the crucial question that is going to come now is to determine the timescales of interconversion between those different states which we're characterizing using experimental NMR data. So we're basically characterizing them in terms of populations, but we'd really like to know what are the energy barriers between them and what the rates of interconversion are and how that correlates with function, because that certainly correlates with function equally as much as the description of the states themselves. So in principle, the same kinds of approaches can be used for folded proteins, and in fact they're a very good idea. NMR ensembles have traditionally been deposited as the result of structure calculations on the basis normally of extensive NOSI data. But these, as you are very well aware, these are equivalent minima to a complex minimization algorithm. And may be correlated, the disorder which is present in these ensembles may be correlated with dynamics, but it may just be correlated with a lack of information, which of course may come from dynamics, but it may not. And of course, other structural biologists and other biochemists tend to interpret the disorder which are in NMR ensembles, which are intrinsic to NMR ensembles, which are deposited in the PDB as dynamics. But of course it would be nice to actually represent the ensemble to represent the true dynamics. And of course we can do that. We know how to do that, we're just a bit lazy and we don't do it. And that, you can see obviously that there are parallels. And of course, protein disorder is a spectrum. Intrinsically disordered proteins, I mean, they're just proteins that have some disorder in them. And two-domain proteins with a flexible linker are also, if you like, intrinsically disordered proteins, probably predominantly ordered. And so it's a broad spectrum, and in principle the same approaches can be applied across the board.